So hi everyone. So we'll just wait for 3-4 minutes and the event can start. So I think we can start. So good afternoon everyone. My name is Musa Rafiq. I'm the course TA for this course CMOS Digital VLSI Design. The course is taught by Professor Sudev Dasgupta from IIT Roorkee. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. So far we have covered 6 live sessions. Now, this is the 8 week long course. Now, only 2 sessions are remaining. In this session, questions will be pertaining to sequential logic design, clocking strategies, and some question about pipelining as well. And in the next class, that is week 8, questions will be mostly pertaining to memory design and few questions from sequential circuits. And then half of the class will be dedicated for revision. So basically, for the next half of the class in week 8, we will be discussing some previous uh, examples. So today is going to be again a very simple class pertaining to sequential design. And apart from that, these are the guidelines. They are as same, but I have to give them again. So please join in with the authentic username. At any point of time, please turn off your camera and microphone. And since the roll is low now, you can always unmute yourself to ask in your doubts. However, if you have some questions, queries, you can always use chat box as well. I'll give you ample time to ask in your doubts. And also, the live session is being recorded, which will be available on YouTube. That link has been already been shared with you guys. And also, I'm talking about the Google spreadsheet. The link will be put after the session is over. And also, the PDF PPTs will be made available. And apart from that, I think we won't be needing any breaks because I think this session will also be short. It won't be that long. And if still some questions remain unanswered or you still have some doubts, you are always free to reach out via email. So the question for today's live session is clock skew in sequential design refers to option A unwanted variation in clock signal frequency, option B the delay difference in the arrival of the clock signal and different registers, after option C the variation in the duty cycle of the clock signal, and option D the sudden failure of a clock circuit. Can anyone tell me in the chat box what will be the correct answer to this question? Yes. So option B, as rightly pointed out by one of the participant, is the correct answer. That is the delay difference between the arrival of the clock signal at different registers. So clock skew can be positive as well as negative, and basically clock skew can be defined as when clock signal reaches different parts of the circuit at different times, potentially causing timing violations, right? Now, the next question, which is also a very simple theoretical question, it asks us what is the purpose of pipelining in a sequential circuit? Option A to reduce power consumption, option B to increase the propagation delay of the circuit, option C to reduce the critical path delay per stage and improve throughput, and option D to decrease the number of registers in the design. Can anyone tell me what is the answer in the chat box? So, what is the purpose of pipelining in a sequential circuit? Option A to reduce power consumption, option B to increase the propagation delay, option C to reduce the critical path delay per stage and improve throughput, and option D to decrease the number of registers in the design. Anyone? So, the correct answer to this is option C. So, I just saw your lecture. So, by that time, I had made my lecture. I think in today morning I saw it. So, pipelining, Professor Dasgupta has discussed pipelining in week 8, but I have put this some questions of pipelining in this week as well, and next week also we'll try to do some questions on pipelining as well. So it's not that difficult. It's a simple concept. So basically, what pipelining is. So let me just draw the definition. Pipelining is a technique So I will read what pipelining is. So pipelining is a technique used in digital circuits, especially in processors and sequential circuits, to increase throughput by dividing a process into multiple stages, each executing a portion of task simultaneously. So this is pipelining is simply inspired by this assembly line packaging. So basically, if you look at the sequential circuit, let's say it consists of multiple combinational circuit blocks or logic blocks, and some of the logic blocks take certain amount of time, some take certain amount of time. So what typically you have seen so far is you want a particular task to be completed in one clock cycle. So as a result, if let's say a particular block A, let's say, takes only units, and particular block take 4 units, so for 2 units of time this block A remains idle. So what we mean in pipelining is we introduce registers, the memory elements, after each of these blocks, such that once logic block A performs computation, it doesn't remain idle. A next set of inputs comes and it performs computation on that. And in the meantime, other blocks are performing their computations parallelly. So I can also define it like this. Instead of in a basically, when we talk about the non-pipeline system, an entire operation is completed before the next one begins, right? Which I already told you. However, in a pipeline system, the operation is divided basically into smaller stages, allowing multiple operations to be processed in parallel. And what happens? A pipeline is structured into stages with registers placed between them to store intermediate results. So you just introduce registers in between and store the values intermediate results. And once the process of intermediate node is done, it will process the next batch of inputs. And as a result, my throughput is increased. So I saw it like Professor Devdas Gupta has discussed this in week 8, but I have kept 2 or 3 questions, pretty simple questions here in week 7. So starting with this question, so it states that not exactly output, the rate at which you process the output, the rate, not the output, the rate at which the output is processed. So if you have to go by the conventional definition, what does output mean? If I talk about this, the throughput of a digital system is the rate at which computes outputs from a new inputs, right? So basically, how many operations you perform in a given time. So that means it can also be said a throughput. In loosely, you can say output per unit time. Loosely, not the exact definition. So basically, the rate at which the output is processed. Exact definition is that. You got it? Is it clear? Okay. So now we have this question 3. It states that if a register in a sequential circuit has a setup time of 1 unit and a clock to delay of 1 unit, how much additional delay does it introduce in a pipeline stage? So basically, the additional delay that introduced by this register will be simply T additional by this register will be simply the clock to queue time and the setup time. That's all. That's the only delay this register will include. And this is 1 unit plus 1 unit. So it is 2 units. So option B is correct answer. So now this question, in fact, you can also find this example in Rabai. I think most of you have referred Rabai, right? So you can always find this example in Rabai. Let me just tell you the exact chapter number. I have book with me. So pipelining, pipelining is in. I saw it yesterday, but somehow it's not here. Just give me a second. In fact, this example is quoted in Rabai itself, so I'm able to find it right now. Maybe I'll tell you later. Okay, yeah. So it is in chapter 7, 7.5. Yeah, 7.5. So For reference, obviously Professor Dasgupta has discussed in week 7. You can always refer to this book, and this example is in fact quoted in there. So the question here we have is, I want part A to be solved by you guys. Part B I'll show you. So part A states that the propagation delay of adder block is 2 units. The propagation delay of mod block is 2 units. Basically the modulus. Basically what this circuit does is it performs the log operation of A plus B. That's all. So the output is basically log of A plus B, mod of A plus B. So the propagation delay of adder block is 2 units. The propagation delay of mod block is 2 units, and the propagation delay of log block is 3 units. The register setup time is 1 unit, and the clock to queue time of the register is 1 unit. So part A, I want you guys to do it. Part B, I'll show you since you are not familiar with the pipeline thing. So you can do part A, and then I'll show the solution. So I'll give you just two minutes. I think more 2 minutes should be ample for this question. So some of the students have given the answer. So just a request, I'll just wait for others also. If you can try part B as well, just try. What do you think will happen? What about others? Have you solved it? So pipelining T min will decrease. That you should keep in mind. Pipelining helps us to reduce the since throughput increases. That means that time will delay. The time will decrease. I'll show you how. Actually, once when I made this lecture, I wasn't aware that you guys haven't gone through pipelining, and I only checked this morning that pipelining is in. So let me just show the solution. So first one is pretty clear as you have done it. So T min basically will be T clock to Q plus T setup plus T PD logic. Just give me a second. I have to attend one call. Sorry about that. Sorry about that. It was some call. So yeah. So first one is pretty clear, right? So first one is T min is equal to T clock to Q plus T setup TPD logic. So it can be written as C clock to Q is 1 unit, and also the setup time is 1 unit. Now TPD logic will be TPD of error adder plus TPD of mod plus TPD of log block, and that is equal to 1 plus 1 plus adder is how much, 2, and mod is 2 and log is 3. So this is 2 plus 7, that is 9. So for first part we got answer as 9 units. Now what happens here is we'll do pipelining. So what pipelining means, after each block we'll add registers. So we have this figure right here, and after adder block I'll have a register, then I have my mod block which will also be followed by register, and then I have a log block which will also be followed by a register. Now what happens because of this? This causes computation for one set of input data to spread over number of clock periods. So basically, when the clock period starts, first the addition block will happen and it will show the result in register. Then it will pass on to the absolute value block, that is a mod block, and the adder block will compute input for the, basically will compute the adder operation for other set of inputs. So once we have this type of case where we have done the pipelining, my T min will be given by like this. It will be given by T setup of register, P clock to Q of register, plus max of T adder block or T mod block, whichever takes the maximum time among the three blocks or the log block. So T setup is 1, T clock to Q is 1, and max of T adder, that is max of T adder is 2, T mod is 2, and T log is 3. So that is 1 plus 1 plus max of 2, 2 and 3 is 3. So it will take 5 minutes. So 5 minutes will be the T min of this. And as a result, that implies your throughput is increased. So if you want to know the nitty-gritties of this example, so what you can do is you can refer to example on page 359. I don't know the version. So, but you can refer to section 7.5. There, this example is given where you can understand in much details. Basically, what you do is you spread your computation over multiple blocks. The main sentence is computation for one set of input data to spread over number of clock periods. So there you can see it's given in detail. Now let's talk about this question, which is given in question number 5. It states that for the sequential circuit shown in figure Q question, that is this figure, delay of each block is 2 units. Mux delay is 1 unit. The clock to Q delay is 1 unit, and setup time is 1 unit. Given the contamination delay is same as the delay values, assume hold time equal to 0. So we have three parts here. So we have to label all the paths. Number 2, we have to determine T min at which the circuit can be operated when clock skew is 0. And number 3 is we have to determine the value of clock skew beyond which the circuit will fail. So how will we do it? First of all, can you guys tell me how many paths are there? How many signal paths are there? I think there is one more path. Can you look for that? So how many paths will be there now? Yes. So let's label them. So first path is simply like this, through register, through logic block, then mux and the output. And then the second one is this path, and the third one is which we call a feedback path, right? Which is like this. So let's label this one as P1, this as P3, and this one as P2. So for first, there are three paths are there. Now part 2 is we have to determine T min at which the circuit can be operated when clock speed is 0. So let's look for P1. What will be the T min? T min for the P1 is basically this thing. So it is T setup of the register, T clock to Q of register plus TPD of logic block, that is each logic block. So 2 into logic block plus 1 of mux, right? So the T setup will be, how much is setup time? Setup time is it given? Yeah, 1. Clock to Q is also 1. So each logic block is 2 units. So it will be 2 into 2, and mux is how much? 1. So it will be 4 plus 5. It will be 7 units, right? Yeah, it will be 7 units. For path P2, let's write P2 here. P2 will be equal to T setup plus T clock to Q plus TPD, which will be consisting of 3 into logic block, these three, and 1 mux. So it will be equal to P2. For P2 it will be equal to 1 plus 1 plus 3 into 2 plus 1. So it will be 2, 8, 9 units. And for P3 it will be T setup plus T clock to Q plus 3 into 2, basically of these three. So it will be 1 plus 1 plus 6. So it will be 8 units. So that implies T min should be equal to 9 units. So because we have to consider the worst, which is this one, P2. Now the question asks us the third part, which I will write here. Third part, determine the maximum value of clock skew beyond which the circuit will fail. So for clock skew path, should I for finding clock worst case clock skew, should I consider the fastest path or the worst case path? So for clock skew, should I consider the faster path or the slower path, the worst case path? No, no. Worst case, when we talk about team in, we take worst case. But for the when we have to talk about the worst case clock skew, we'll take the faster path, because if you talk about this clock skew, it gets subtracted, right? Subtracted. So violation will happen when there is a faster path. So let me show the condition. The condition for that is T clock to Q plus T set to TP logic should be greater or equal to delta plus hold time. I think, have you guys seen it? This condition where h is your hold time, but in our case h is 0. So that implies delta should be less or equal to clock to Q is how much? 1 unit, and TP logic for the faster path is 3. That is how much? This one. This is a faster path, right? 2 plus 2, that is 2 plus 2 plus 1 and mux, yeah. So that is 2 plus 2 plus 1. So delta should be less or equal less than 6. So the circuit will fail if skew exceeds 6 units. So here, let me write in brackets faster path. So how you define this skew? So you have seen the timing definition. How does the timing definitions change? T min minus delta, right? So if it exceeds the faster path, then there will be timing violation, right? You see this delta equal to 6 units. If you take other two paths, they still satisfy the constraints, right? But for the faster path, the constraint is not satisfied. Yeah, got it. So for this case, it is 6 units. Now we will move to this question, that is question number 6. So before proceeding, can anyone tell me what type of circuit is this? What is this circuit? Have you seen this circuit? Anyone? Has anyone seen this circuit? Or can anyone comment about this? Let me make it slightly bigger. Yeah. Yes or no? No will also work for me. Not really. Yes, yeah, it is master slave configuration. Exactly. It is master slave. I think you are close. Yeah, it is master slave. Yeah, let me just talk about it in detail. But before that, let's recapitulate some of the things. What is this? This block? This is an this is a symbol of correct inverter, and this thing transmission gate. Yeah, thank you. So I think we are ready to go. So what the circuit in front of you is, it's basically a master slave edge triggered register. This is the most common approach for constructing an edge triggered register. So this is a transistor level implementation, but if I have to talk about its implementation in terms of mux, basically it's mux based. I will tell you where the mux is. So this is basically like this. So what is this? Can anyone tell me what is this? The thing that I highlighted. The thing that, yes, it is a negative latch. Thank you. So it is a negative latch, and the other one is a positive latch. So this thing that I have shown you to you is basically the master slave edge triggered register. It consists of a cascading of a negative latch, which is made up of a master stage is made up of a negative latch. So this entire thing is your negative latch, and that one is your positive latch. And here a multiplexer based approach is used. So multiplexer based approach is used. So what happens? So when the clock, when the clock is low, the master stage is transparent. So by transparent, it means the output D will be fetched here. So here output B will lie. This point is called QM. So it will be transparent. So it will be on. So D will propagate to QM. So exact wording is on the low phase of the clock, the master stage is transparent, and the D input is passed to the master stage output that I said is QM. During this period, the slave stage is in hold mode. So whatever the previous state was, it will be keeping maintaining its stage. So how it maintains? Using the feedback that you already know. So once the rising edge of the clock occurs, the master stage stops sampling the input and slave stage starts sampling. And during the high phase of the clock, the slave stage samples the output of the master stage, that is the QM, while the master slave remains in hold state. As the QM is constant during the high phase of the clock, the output Q, that is this output Q, will only make one transition per clock cycle. Since the value of Q is the value of D right before the rising edge of the clock, this is a positive edge triggered effect. So this is basically a positive edge triggered master slave configuration. How we can achieve the negative edge triggered? Can anyone tell me how we can achieve the negative edge triggered? So negative edge triggering can be achieved by simply swapping the positions of positive latch and negative latch. So here the first one is the negative latch and the second one is positive latch. By swapping these positions, you will have a negative edge triggering. This right here, this circuit is basically the transistor level implementation of master slave positive edge triggered register. Multiplexer is basically implemented using transmission gates that you already know. So what happens here is when the clock is low, T1 is on and T2 is off, and D input is sampled to Q node. So D into QM node. During this period, T3 and T4 are off and on respectively, and the cross-coupled inverters I5 and I6. So basically this one cross-coupled inverters I6 and I7 hold the state of the slave stage. Basically, because of these two inverters, cross-coupling of inverters, the slave state maintains its states. When the clock goes high, the master stage stops sampling and it maintains a hold stage, and the slave state starts sampling the input. So what happens here in the when the clock goes high, T1 is off and T2 is on, and here T3 will be on and T4 will be off, and QM will be copied to Q. So that is the entire operation. And if I have to draw the timing diagrams of it, so they will look something like this. This is D, this is clock, and here will be QM. Let's draw QM here. You can refer to Rabai for the better drawing. I'm not very good at this. So just to give an idea, whatever we have discussed so far. So this is your timing diagram. Now, in terms of the timing constraints of this block, So basically, three things are to be there: the setup time, the hold time, and the propagation delay. The setup time is defined as the time before the rising edge of the clock that the data D must be valid. So basically, how long before the rising edge my data should be stable such that the QM samples reliably, such that this is sampled reliably. So basically, the setup time here is given by the input D passes through D2, then T1, then I3, and then we have to also take care of this I4 thing. So basically, all three inverter delays and one transmission gate delays. So what happens because of this is when we take these delays into consideration, this ensures that the node voltages of both the terminals of transmission gate T2 are at same value, right? So they are at same value. Otherwise, it is possible for cross-coupled pair, that's this one and this one, to settle to an incurrent value. Thus, the setup time is given by I2 plus I3 plus I4 plus transmission gate T1 time. So this is my setup time. And the propagation delay is defined as the time it takes for the value QM to go to the output Q. And this is given by T clock to Q is given by the transmission gate T3 plus the inverter I6. I have a question here. Since I defined a propagation time delay, it should be basically the time taken for QM to go to Q. And here I defined T clock to Q as time of this block and this block. Why haven't I considered this thing, this inverter time consideration? Can anyone tell me why I haven't considered this inverter's delay in the propagation delay time, the clock to Q time? I define propagation delay as time it takes for QM to reach to Q. It passes through I3 as I5 as well, but I haven't taken it into consideration. Why? The answer lies in setup time. Can I now I have given you a hint as well. So the reason is that as we have already included the delay of I4 in the setup time, the output of I5 is valid before the rising edge of the clock. So that's why we haven't included this thing because we have already included I4's delay and I5 delay will be incorporated in that part as well. Regarding hold time, the hold time represents the time that input must be held stable after the rising edge of the clock. In our case, the transmission gate T1 turns off when the clock goes high. As you can see, it turns off when the clock goes high. Since both the D input and the clock passes through inverters before reaching T1, any change in the output after the clock goes high does not affect the output. So in reality, the hold time is zero for this configuration. Now, since we have an idea about this, the only thing is just to plug the values. So, so far what we have found here is the master slave edge registers. Setup time is given by this thing. So it is basically 3 into TPD of inverters plus TPD of transmission gate, right? So it is 3 into how much is TPD of inverter in our question? It's 1.5. No, it's 1. It's 1. So it's 1 and transmission gate is 1.5. So it will be 3 plus 1.5 is 4.5, right? And T clock to Q will be equal to T3, that is transmission gate 1.5 plus I6, that is 1. So that will be 2.5 units. So the idea is the clock to Q, the propagate this setup time is basically the delay here encountered here in this feedback path and the clock to Q delay is this much. This is also given in Rabai. If you want, you can refer. Let me just check the page number. This the section number. Just give me a second. So this will also be in chapter 7. So this is in chapter 7 in section 7.2. So this is 7.2, where you will first find the multiplexer based latches, and then you will have the master slave edge triggered register. This was question number 5. Okay, okay, this was question number 6. Now question number 7 I have for you guys. So the question 7 states that a processor operates at 500 megahertz with a clock jitter of plus minus 100 picoseconds, right? What is the worst case change in the clock period? So can you guys solve it? It should not be that difficult. Has anyone done it? This is a pretty simple question. Has anyone done it? So let me just give you a hint maybe. So what will be T of this thing? It will be 1 by 500 into 10 raised power 6. Basically T is 1 by T is equal to 1 by F, right? So it will be 1 by 500, that is 1 by 5 is 2.5, 1 by 0.5, 0.2 into 10 raised power 8. 10 raised power 8 equal to 2 nanoseconds. And how much is jitter? Jitter is plus minus 100 picoseconds. So the worst case jitter that we can experience is plus minus zero point 0.1 nanoseconds, right? So the worst case time period will be simply t plus minus zero point 0.1 nanoseconds. That is equal to either it will be 2.1 nanoseconds or 1.9 nanoseconds. Right? Got it? Now, there is this question. An 8-bit triple carry adder is adding the following bits. So 0 and then ones, and B is 0 and at the end LSB is 1. So part 1 says that does this input correspond to worst case delay? Justify your answer. So I want you guys to answer whether will this input case correspond to a worst case delay? Yes or no? Anyone? Will this input case correspond to a worst case delay in 8-bit triple carry adder? A ripple carry is, yeah. So you know ripple carry, the carry propagates, right? So you have this adder block, full adder block. You get the sum, you get the carry, and that carry goes to the next full adder block, and then it propagates. So if you clearly examine this A and B, it is 0, 1, 1, 1, 1, 1, 1, 1, and this is 0, 0, 0, 0, 0, 0, 0, 1. And once you do the addition, you see carry propagates to the last bit, and the result, it is a worst case scenario because carry propagates all the way to the end. So it is worst case as carry propagates to last bit, right? Now now can you tell me what will be the delay in this case? Can you guys figure out what will be the delay? So let me just tell you. So delay in the worst case scenario will be n minus 1 times t carry plus t sum. So n here is 8, so it will be 8 minus 1.5 plus zero point 0.5. So it will be 3.5 plus zero point 0.5. That is 4 units. Is this clear? So if that's clear, I think we can proceed to our last question of today's live session. So this is again based on that master slave configuration, but it has two parts. And I'll just read the question for you. I want you guys to do it. So this is simply question we have done in, I think, question number 6 that was, or 7. Uh, this one. This is exactly, it will follow the same methodology. So no, it will not be the worst case. So, question 9 says that a student wired mux-based master-slave register as shown in this block. So this one is part A, this one. Ignoring the delay, basically the clock delays, ignore them. This I12 and I6. I12 is this one and I6 is this one. Ignoring them, ignore them. We have also ignored them previously. So the what will be the setup time of circuit and the clock to Q time of the circuit? Do this part first. Come on, do it. I think it's simply just plugging the values. By now, you should be able to do it if you got this one. Maybe for reference, I'll keep it here for just a couple of seconds. And exactly same methodology you have to adopt here. So, and inverter delays are 1.5 units and transmission delay is 2.5. So, TG is 2.5 and TI win is 1.5. So, do it. Find the setup time and find the clock to Q time. If you remember the formula, you will just give the answer right away. But if you have got, if you know the concept, you will just look at the circuit and you can also figure out what will be the delay. Okay, this one. Is it better now? It's exactly the same circuit as it was previously. It's just the orientation has changed. Correct, correct. Yeah, that's correct. So here input D, so the setup time will be like this thing, and QM to D will be this thing. So basically T setup will be equal to T of I1 plus T of T1 plus T of I2 plus T of I3. So basically 3 into 1.5 plus 2.5. So 4.5 plus 2.5 is 7. And T clock to Q will be equal to T of T3 plus T of I8. So it will be 2.5 plus 1.5, that is 4. Now part B, what part B says us? The register in A, so this whole thing is a register simply is used to make a sequential circuit in this thing. So here it is used as a resistor. Now what we have to do is we have to obtain T min of this thing. So copy and paste. So the registers is simply what we have evaluated previously, and now we have to find the T min. So what will be T min of this thing? Where the registered is this one. This one is a register, and logic block has propagation delay of 6 units. So TPD logic is 6 units and register you have found previously. So what will be the T min of this sequential circuit? I think this is the most easiest question you'll have. I think so far you have done multiple questions based on this. So T min of a sequential circuit, how is it given? T min is equal to T setup plus T clock to Q plus T propagation delay of logic, right? Now fill in the numbers, you'll get the answer. So what is the answer? Yes. So T setup is 7, T clock to Q is 4, and TPD logic is 6. So it will be 17 units. By the way, if clock skew was present in this circuit, what will be? Whether will it be a positive or negative clock skew? If there was a clock skew, will it be a positive clock skew or a negative clock skew? So negative. Why? What is the reasoning? Yes, directional data and clock are opposite. And does negative clock skew lead to any timing violations? So, what you can do for an exercise, look for it. What I will suggest is, Rabbi has C is more than positivity on. So, what I'll suggest is, yeah, I got your point. So, what I'll suggest is, you can look for the timing definitions in Rabbi. It's very well explained, and how what is I think explanation. If you have any doubts, you can always refer to the Rabbi. And Professor Dusk has also explained it really well. So that was all for today's live session. But before closing the session, uh, first of all, are there any doubts in today's lecture? Let's just address them. So if not, so if so, I don't know whether Professor has discussed sizing. Sizing. So I know sizing. I remember last time I discussed it in week 4. I think once I gave you the sizing. In fact, we discussed one question of sizing as well, and then there was one more question of sizing. But some I that time told you that You haven't studied about sizing, so we will not touch that. But I don't know whether professor has touched upon sizing or not. Has Professor Dasgupta discussed sizing of transistors in combinational logic, right? So basically, in combinational circuit, CMOS circuit, has Professor Dasgupta discussed sizing of transistors? Anyways, if he hasn't, or it doesn't matter. So what my plan is, basically next week is week 8, and typically there used to be an extra session where we used to have a revision lecture, or a revision where we used to solve problems from the previous classes, and in fact add some more problems. But this time I'm not available. I have some busy with some work. So what I'm planning to do is, so week 8, when we have the problem solving session next Sunday, first half of 40 to 45 minutes we will devote to VKIT's contents, and then I'll pick some problems from the previous live sessions which I think will be important, or have some are difficult, or covers most of the concepts. I'll pick them, and even I'll pick the problems that have been discussed in this year's assignment. So if the obviously due date is passed for will be passed for at least for assignment number 7, so I will can discuss them. So last time I had asked if there are any questions you want me to discuss. So one question is sizing one. I'll just take a note of it somewhere. So sizing one, I'll try to keep one problem on sizing, which is, in fact, sizing is a really good topic, to be honest. So sizing, one problem I'll keep on sizing. And other than that, is there any problem you want me to discuss from the previous live sessions or assignments? Please let me know. If you don't have any idea right now, you can email me, or and I'll put them in the lecture slides next time. And if you know the problem right now, please let me know. I can give you a couple of minutes if you want to look. Otherwise, we can close the session. So, to the participant that was asking about transistor sizing problem, it's the same thing, right? That I explained, right? That time I told you we'll skip it. Was it the same case, or is it something different? Yeah, I remember that time. I showed you two problems, but somehow you are not able to grasp that. Yeah, I'll discuss it, no issues. And is there any other problem you want me to discuss? I see some of the participants here, they are regular at least, so maybe they can. Yeah, Nora. Nora, in fact, I discussed it twice, but still, Nora and transmission gate problem, transmission gate problem. I think I showed you the implementation of sum and carry block using transmission gate logic, right? No, that was past transistor logic. Sorry, sir, that was past transistor logic. I think I haven't discussed any problem on transmission gate, right? So yeah, that's something we can touch upon. Transmission gates. We can have one problem on transmission gates. Nora, so Nora, I'll take the previous problem. I will discuss the previous problem that we have already discussed. We'll touch upon that uh, this time as well. Sizing, I'll see whether I'll have a new problem or the previous problem. And transmission gate is something we haven't discussed that I can remember. Yeah. Any other participant, any other thing you want me to discuss next time? So these are nearly 3 questions. We can still have 3 more questions which we can discuss. At least 3 more because we have to discuss week 8 as well. If you are not able to recall it right now, you can always email me. But please let me know before Saturday, right? Then I can make my lecture accordingly. So I think that was all for today's live session. See you next time. Thank you for joining.